So we've talked about systems of particles that have no internal structure, that just have a position coordinate x. What happens if they also have some internal structure? So this might be some spin, if it's say an electron, or it might be the electronic states of say an atom or a molecule. Anyway, what that means is that the Hilbert space is going to have some extra degrees of freedom. And in my case, I'll label those extra degrees of freedom with the index j, and our basis states now have a j and an x. And of course, the Hamiltonian is also going to have some j dependence. And so what we've done there is you'll note that we have assumed that the kinetic energy term does not change this j index. So the j index there and the j index there are the same, and we're just taking the diagonal terms in terms of j. But we're not assuming that for the potential. So the potential might be able to take a state with the extra structure index L and change that extra structure index over to a K. And as usual, once we have the single particle Hamiltonian, getting the many particle Hamiltonian is straightforward. And we get it in terms of the many body creation annihilation operators. And of course, we're now creating and annihilating particles with not just a position x, but also some kind of index L. You might ask, why didn't these states also have the option of changing x to a different value? And you can certainly write an operator that does that, but physically that's very rare. That means particles can instantaneously teleport across space, and that basically doesn't happen. That's a property of causality. So when you have special relativity, those kinds of terms aren't allowed to exist. Putting all that into the position basis, we get something like this. We introduced a delta function in order to make sure we didn't have any accidental cross-coupling between the different internal structure states for the kinetic energy term. Now what we don't have here is we don't have any interactions between the particles. Remember, we built this up from the Hamiltonian for one particle. If we had a Hamiltonian that included interactions between pairs of particles, then we'd also get extra terms that had pairs of creation operators and pairs of annihilation operators, and they would tend to look something like this. And again, we have a restriction where rather than being able to take any two particles at any two positions and then turn them into two particles at any two other positions, because of causality, we're making sure that if we take a pair of particles from x and y, we create a pair of particles at x and y. So that gives us some restrictions, so we only have two coordinates in our coefficients. So we have action at a distance, but not teleportation. So that's a fairly general kind of Hamiltonian for a set of multiple particles. We do try to make approximations beyond that if we can, of course. Now at low temperatures, the particles often don't have enough energy to really probe the details of that interparticle interaction, and so we can make a very powerful approximation, which is called the contact potential. It's where you replace the potential between two particles with a delta function. So we're assuming they can come right up to each other and then they bounce off. So the entire potential is now just characterized by a single number, and that single number is related to physical parameters in the following way, where m is the mass of the particle, we've got h bar, and that a is called the scattering length, which is really just the natural length scale of the interaction. Now the really nice thing about delta functions, of course, is that they interact very well with integrals to get rid of the integrals, so we can write our Hamiltonian in the contact potential approximation to be, and everything looks completely local.